Hello, Mr. Claudia here. Today we are going to continue our study of univariate analysis. That is, we are going to continue our analysis of single variable data by measuring spread. Now, a few lessons ago, we looked at how data can be spread out. We divided it into four sets, the quartiles, and we looked at range and quartile ranges and interquartile ranges and box and whisker plots. The problem with measuring spread that way is that you only ever consider four values or three values, right? These Q1, Q2, Q3. Doesn't really it doesn't involve a calculation that includes every number in our data set. And so we'll write that out, right? Like, oops, I'm in the wrong color here. IQR, for example, is just two numbers. It's the Q3 number minus the Q1 number. Range is just the max minus the min. What about all the other numbers in my data set? They're just kind of ignored. So we're going to try today to figure out a way we can use all of our data and how spread out the data is. So consider these two groups of data. So let's start with the first one. The class average, these are all, say, average marks, or these are all your marks. The class average is 77 here. So and then the class average here is 77 as well. Now what's the difference between these two groups? Well, I think you can see by looking at these two simple data sets that these numbers are a lot closer to the average, 77. They're closer to the mean. Whereas these numbers have the same average, but they're further from the mean. So if you want to imagine this like kind of visually, which is not something we really do, but let's just to give you an idea, we have 77, which is the mean, and then we have, we have this point 74, we have 75, we have 76, and then we have 77, and then we have a point over here which is 80. Oh, we have another one that's 80. So you get a sense that they're all pretty close and that these are balanced by these ones over there. That's why 77 is the average. Whereas for this data set, 77, my average is here. Well, 54 is way over here. 86 is pretty far up. And 91 is even further. So these two are balanced by that. Sure, the average is 77, but they're way further away from the mean. So the way we're going to measure spread is there a way I can add up how far each of these numbers is from the mean? Because that'll tell me that these are a lot closer than these. So let's try doing that. Let's try finding the distance, put distance in quotation, from the mean for each point. So for example, 74, well, 74 take away 77, that is -3 away. 75 take away 77, that's -2 away. 76 take away 77, that's -1 away. 80 subtract 77 is +3, and we do it twice, right? So that's what we were doing there. We were calculating the quote-unquote distance from the mean to each of these points. And the numbers are really small because they're really close. Now if I go over here, I do the same process. I have 54 minus 77. That is -23. 86 minus 77, that is +9. And 91 minus 77, that is +14. So you can see these numbers are obviously a lot bigger. Okay, now if I want to look at the whole data set and figure out which data set is better, I would have to add up all of these distances. So I get -3, -5, -6, plus 6, I get 0. And if I add these up, I get -23 plus -0. Interesting. They both add up to 0. Well, this shouldn't be too much of a surprise. We know that the mean is in the middle. So if I add up all the numbers that are to the left and all numbers to the right, they're going to balance, the distances are going to balance each other in both these cases. So this makes sense. But it's not great, right? Because when I add up all this information, all these distances, I don't have any information about the spread of the data, because 0 and 0 doesn't distinguish these two data sets from each other. So why is this happening? Well, this is happening because this is a negative number and this is a positive number, and so they balance off each other, or they balance out each other. So what I need to do is get rid of the negatives and repeat this process. So to eliminate the negatives, we square the differences. So do you see what we did last time where we found these differences? Well, we're going to take those numbers and we're going to square them. So negative 3 squared, negative 2 squared, negative 1 squared, 3 squared, 3 squared. Negative 3 squared is 9, 4, 1, 9, 9. Then I'm going to add up all of those. So 9 times 3 is 27, 31, 32. Over here I'm going to do the same thing. Negative 23 squared, 9 squared, 14 squared. Those I'm not as skilled with. I have to do it with my calculator. 23 squared is 529, 81, 14 squared, plus 81 plus 529. That gives me 806. So there. Now we have a way of analyzing the spread of the data. This number, you can see the spread is very small. Like these differences are very small, 32. Whereas these 3 data points, the number is a lot bigger. It's huge. So I know the data is more spread out. Now the only issue here is you might be saying, well, this isn't really fair to compare these 2 data sets because there's only 3 points here and there's 5 points here. Like it's not fair that you're comparing this number when that they're not the same size data set, which is true. So you should actually divide by the number of data points. So here is 5, here is 3. So 806 divided by 3 is 268.7, and over here I have 32 divided by 5, which is 6.4. So there we have it. We have found a way now to measure the average distance from the mean. And now when you do that to a data set, now you can compare data sets and compare this value and see this is a lot more spread out than this data. What we've just found is called the variance. We write sigma squared is equal to sum, big sigma, from 1 to n of x sub I minus mu squared over n. Wow, where did all the numbers go? Well, this is just a mathematical representation of what we just did. So we took each data point, x1, x2, x3, x4. For each of those data points, we subtracted the mean, or the average. So we took the first data point, subtracted the average, we squared each of those, and then added them all up. Right? So I took 54 minus the average, negative 23, I squared it. I added that to 0.86 minus 77 squared, and I did that, and I got my total. So I added up all of those squareds. Then I divided by the total number of points. In this case, I divided by 3. That's called the variance, and it's a way of measuring the spread. We write sigma squared, right? This is little sigma. Just like in the English alphabet, the Greek alphabet has capital and lowercase. So this is sigma, but lowercase. The variance is great. It tells us the average distance from the mean. But what we actually prefer is to use standard deviation, which is the square root of variance. So we're just going to write that out again. The standard deviation is preferable, so it's the same thing, it's just a square root, because once we take the square root, now we have the same units as what the data we started with. Here you can see that when I squared everything, I got these massive numbers. So like even over here, 268 doesn't make any sense when we're talking about averages that go up to between 0 and 100. If you take the square root of this, so the square root of 268, you end up with 16, which is a number that it has the same units as the average that we were dealing with. Those are the numbers we were dealing with. So standard deviation is preferred. And you're going to hear this number come up a lot, especially in a few chapters from now. Actually, here's a preview right now to chapter 5, 6. So this is a preview to chapter 6. But standard deviation is useful because we will learn that 68% of data usually falls between mu plus or minus 1 standard deviation. So we're going to learn this in chapter 7 or chapter 6. But here's all the data for some data set. There's the mean. And we find that most of the data is plus or minus 1 standard deviation. Then I think 95% is between plus or minus 2 standard deviations. To give you an example, consider if I measured the heights of every student in this class, and the average was 5'8". That would be my average. Well, 68% of the students would be within the average plus or minus the standard deviation, whatever the standard deviation is. So standard deviation is something that's going to come up, and it's very useful. Just a few notes about standard deviation. It is very sensitive to outliers. Because of the squaring impacts, because of the squaring that's used in the calculation, the number can be really affected by an outlier. And you saw that here, right? These differences, this guy who had a 54 creates a really massive variance and a really massive standard deviation. Secondly, standard deviation is most useful for symmetrical data. So usually, if you have all the data, skewed somehow, so a lot of the data is in the small end or the upper end, it's going to mess up your standard deviation. It's nicer if you have good symmetrical data. Okay, let's start using this new thing that we just discovered, and we're going to calculate a few of these by hand. So in this example, we have a group of 5 students who were chosen from each of 3 schools. The students were given a series of puzzles and 2 hours to solve as many as they could. How many did they solve? Find the mean and the standard deviation for each school. So this school, 5 students were selected. They each did 7 puzzles. They each completed 7 puzzles. The mean is the average, so I would add up 7 plus 7 plus 7 plus 7, divide by 5. 7 times 5 is 35, divided by 5. Well, no surprise, this should be 7, right? The average is 7. Now, standard deviation. Well, sigma squared. Let me start by finding the variance. Remember the process. If you don't like that formula, just remember the process. I take each data point, subtract the mean, square the answer, and do that for each data point. So I have to do this, essentially the same thing, 5 times in this question. Then you divide by 5. So I end up with 0 plus 0 plus 0 plus 0 over 5, which is just 0. The standard deviation is the square root of that answer, so square root of 0, which is 0. So look at school A. All the students did the same, so their average is all 7. The standard deviation is 0 because the data is not spread out at all. The next school, there's more of a range. The students did different amounts of puzzles. So to find the average, I have to add up all these numbers and divide by 5. 5 plus 6 plus 7 plus 8 plus 9. Oops. 5 plus 7 plus 6. Can't seem to use my calculator correctly. 35 divided by 5 is 7. Let's find sigma squared, or the variance. We'll use the same strategy as last time. I take the first point, subtract it from the mean, which is 7, square it. Do it with the second point, 6 minus 7 squared. Do that with all 5 points, and then divide by 5. Okay, let's see if I can do this with my calculator. So 5 minus 7 is negative 2 squared, negative 4. Then this is going to be negative 1 squared, so plus 1 squared, plus 0 squared, plus 1 squared, plus 2 squared again. Divided by 5, that gives me a standard variance of 2. Now the standard deviation is the square root of that. Root 2 is approximately 1.41. So we see for this group they have the same average, 7, but the standard deviation is 1.41, indicating that there is some spread to this data. It's not as tight as, well, it's not all 7s. This data for school C, same thing. I add up all of my data points, divide by 5. 3 plus 5 plus 7 plus 9 plus 11 divided by 5 is 7. No surprise, it's still 7. Or it is a surprise maybe to you. Okay, sigma squared, the variance. I take each point, subtract from the mean, which I just found, and I do that for each point. And then I divide by 5. So let's see if I can do this. So this is going to be, now really doesn't matter the order. Like if I had done 7 minus 3, because I'm squaring it, it doesn't matter. And if like right, the negative 4 or positive 4 squared is the same. So it's 4 squared plus 2 squared plus 0 squared plus 2 squared plus 4 squared. And that gives me 40 divided by 5, which is 8. Standard deviation is the square root of 8, which is 2.83. You can see this data has the same average, but the standard deviation is large, showing that there's much more spread in this group versus this group. Note again that this number, standard deviation, includes every single student's work in its calculation. That's why we like the standard deviation so much. Also note with the variance, here I had a variance of 8, which is like thinking, well, 8 puzzles squared, like, well, this is really large compared to all these values. That's why we prefer the standard deviation. This is saying that each student did 7 puzzles plus, or no, the average is 7, and then the standard deviation is 2.83 puzzles. That's how spread out the data is. Okay, let's do a larger sample now. Below you have the sample of a number of children taken at random from people in the city. Okay, so every time I do this, I always have trouble. It's the number of children, comma, taken at random, comma, from people in the city. So it's not children who are kidnapped, it's number of children that people have in the city if I take a random sample. Find the sample mean and standard deviation. So, okay, just to be clear. So we have the number of children. So 12 people have 0 children, 16 have 1, 11 people have 2 children, then yeah, there's only one person that has 4 children. If you want to write out the data just so it makes a bit more sense, it's 0, 0, 0, 0, 0, 12 times, and then 1, 1, 1, 1, 16 times, and then 2, etc., etc. So there are 12 zeros, 16 ones, etc. So when I draw a table like this, when I write a table like this, it's just representing all this data, which is a lot of data points, in a tidier way. So we need to find the sample mean. I'm going to find the mean over here off to the side just so it doesn't get in our way, because the mean is no, we'll come back to the mean. Okay, let me show you how to use a frequency table to assist you in this calculating these two things. So this is my statistic, the number of children. The possibilities are 0, 1, 2, 3, and 4. This is my frequency, which is not a statistic. It's just the number of times each thing exists in my list. So remember when we studied mean, central value, I really want to take 0 and multiply it by 12, plus 16 or plus 1 multiplied by 16. Instead of adding all these pieces one by one, I can just use some multiplication to help me out. So what I'm interested in finding is x times f. And you did this when we did our finding mean. So 0 times 12 gives me 0, 1 times 16 gives me 1, 2 times 11 gives me 22, 3 times 3 gives me 9, 4 times 1 gives me 4. If I add up all those values, I get 1, 20, 23, 31, 30, 32. Wait a sec. No, this is 16. Sorry. 1 times 16, 16, 16. So this is 38, 47, 51. So if I were to just add up all of the points, I get 51, but I used some multiplication to make my life easier. And then I divide by the total number of points, the number of data I collected. So That would be frequency. 12 plus 16 is 28, 29, 39, 43. So 41 children divided by 43 people surveyed. So 51 children divided by 43 people surveyed is 1.1860, approximately equal to 1.19. That's the average number of children. Now, we can't have 1.19 children. That means you have one child and then an arm. But it's an average, right? So we understand that this means that on average, each person in the city has a little bit over one child. Okay, that's the mean. Now, and also I rounded the three significant figures. Now, what I want to figure out is the spread of the data. So I'm going to use the standard deviation strategy I just did up here. I'm going to take each data point, so 0, subtract the mean, 1.19. Then I'm going to square that answer. Then I'm going to do it again with 0, then 0, then 0, then 12 times of that, then 1, then 1, then 1, then 1, then 1. So you can see this would be very repetitive, but because some of these things happen many times, I can figure out the answer once and then multiply it by the frequency. So let's do the next column, we'll do one step at a time. So first we're going to do the samples, or the data. So 0, subtract the mean, which is 1.19. Now, I would not use 1.19 in my calculation because this is the rounded number. I would always use a number that has a few more significant figures. So I'm going to use 1.186. This is going to give me more accuracy. If you use the rounded number, you're throwing away some of your accuracy and your final number will be a little off. 0 minus 1.186 is equal to negative 1.186. The second value is number of children was 1 minus, again, the mean. And this gives you negative 0.186. Then you had 2 minus 1.186. 2 minus 1.186, which is 0.814. Then you had 3 minus 1.186, which would give you 1.814. And then you had 4 minus 1.186, which gives you 2.814. Now this amount, negative 1.186, you have to add that 12 times. So, first I have to square it. So I'm going to take those values, and I'm going to square them. So 1.186, I'm really having a hard time today with my calculator, sorry. 1.186 squared equals 1.407, let's say. I'm going to round it to more than 3 significant figures, so I carry an extra significant figure. 0.186 squared is 0.0346. Then I have 0.814 squared, which is 0.6626. 1.814 squared, 3.291. I know there's some tendency to want to write down every digit here as well, but that's also impractical because then you're going to have to write down so many numbers and there's more chance of making an error. So I would recommend to just always carry one extra digit, maybe 2, more than 3 significant figures. Okay, so now this number, 1.407, I have to add that 12 times. So what's quicker is to take the frequency multiplied by x minus mu squared. So I'm going to take each of these numbers and multiply it by the frequency. So this one's going to be 12 times 1.407. 1.407 times 12. So that gives me 16.884. 0.0346 times 16. That gives you 0.5536. This is so much fun. 0.6626 squared, which gives me 0.4390.
3.291 squared, which gives me 10.83. Let me just double check that. 3.291 squared, which gives me 10. Okay. Then I have 7.919 squared, which gives me... Oh, I'm not doing this correctly. Oh boy, I'm making mistakes. 0.5536 times 16. Sorry, that should be... Oh boy, Mr. Claudy. Oh, and this is all being recorded. Sorry, I was supposed to take these numbers, 0.0346, and multiply by this number. So that gives me 0.5536. Okay, this one I take the squared, 0.6626, and multiply it by 11. That gives me not this number that I wrote here, so sorry, should be 7.293. Then here I took 3.291 and multiplied it by 3 data points. So that should be, there we go, 9.873. Finally, this last one, I just do it once, so I don't have to do any multiplication, thankfully. Okay, so now I have all of these squared values. I need to now add all of these up. So 16.884 plus 0.5536 plus 7.293 plus 9.873 plus 7.919. That gives me 42.523. Oh, okay, now we have it. Variance is equal to that number, that addition of all of those squares, divided by the total number of points, which is 43. So I get 0.989 for my variance. My standard deviation is the square root of that number. So I just take the answer, it's still in my calculator, I type square root, and I get a variance, or a standard deviation of 0.994. So for all these, this city that we just analyzed, the average number of children is 1.19. And the standard deviation, the spread of the data is plus or minus, is one child basically. It's 0.994 children. So that if you went to another city, calculated, did the same survey, you might have a slightly different average, or you might have a slightly different standard deviation, telling you that the data is more spread out. Okay, we're just going to make one little note here. I mean, this was a fun example, right? We got to do so much math. You are going to have a quiz, hopefully, on this, where you're going to have to do this sort of work by hand, because it's a good experience to go through once in your life. But you're never going to compute variance manually, like we just did here on an IB exam. You're going to always use the GDC. So did you see what we did here, where I gave you some data and we wanted you to find the variance and standard deviation? If you get an IB exam, you will always use the GDC to do this. You will never do this process. I will get you to do this process once on a quiz just to show me you can do it, but thereafter we'll always use the GDC. If you do something like this manually on an IB exam, you're wasting your time, because it takes 15 minutes and with a calculator it takes 2. We'll show you that GDC lesson later. There's one other thing I want to talk about with the standard deviation and mean, which is what happens when you make changes to the data. So for example, go back to school C. What happens if each of these students solves one more puzzle? In other words, if I add 1 to each of these numbers. Well, my new data is going to be 4, 6, 8, 10, and 12. Now let's find the mean. Well, it's going to be 4 plus 6 plus 8 plus 10 plus 12 divided by 5. 10, 20,
30, 40 divided by 5, which is 8. The standard deviation, or the sigma squared, or variance, I'm going to have to take each number, subtract from the mean, and square it. And if you do that, you get, what's this going to be? 4 squared plus 2 squared plus 0 squared plus 4 squared plus 2 squared divided by 5. You also get 8. The standard deviation is the square root of 8, which is going to be 2.83. Same thing we had last time. So look what happens. This is a little point that IB likes to test you on. If you have a data set and you add a 1, or you add some amount to each point in your data set, look what happens to the mean. So I added 1 to each point in my data set. My mean went from 7 to 8. It went up by 1. My standard deviation, on the other hand, was 8, or is 2.83, 2.83. My standard deviation didn't change. Because essentially, when I add 1 to each data point, my average moves, but the spread of the data stays the same. So, as a rule, adding or subtracting a constant k to a set of data increases or decreases mu by the value k, by the amount that you added or subtracted. There is no change to sigma, standard deviation. What if each student solves 10 times the number of puzzles? So if I take my original data and multiply each of them by 10, so then I get 30, 50, 70, 90, 110. Well, we've done this a million times. Let's find the average. That's 30 plus 50 plus 70 plus 90 plus 110 divided by 5. Well, let's just do it by hand. 80 plus 70 plus 200 divided by 5 gives me 70. Interesting. And for the variance, I would take each value and subtract the average, square it, do it again, square it, and divide by 5. So if I do that, I'm going to get, 40 squared plus 20 squared plus 0 squared plus 20 squared plus 40 squared divided by 5 gives me 800. So the standard deviation is the square root of 800, which is 28.3. Okay, so what happened? Well, if I multiply all my values by 10, my average goes from 7 to 70. So I multiplied my average by 10 as well. And for my standard deviation, it goes from 0.994, 2.83 to 28.3. So it also gets multiplied by 10. Note, however, that my variance, which was 8, is not multiplied by 10. It's actually multiplied by 10 squared because it's a variance, right? So just be careful. The standard deviation is multiplied by 10. The variance is multiplied by 10 squared. So let's make a note there. If you multiply or divide a set of data by a constant, you're going to multiply or divide the mean by that constant, and you're going to multiply and divide the standard deviation by that constant. As for the variance, well, if you really cared, you would have to divide the variance by the value squared. Phew. So there you have it, a new amazing way of looking at the spread of data. And this is the one that we're going to come back to in future chapters. So this is the one that tends to be the most used and the most commonly heard. So your homework is page 279, number 1678, and page 281, number 3. And just to be clear, we're not using the GDC. I've only assigned a few questions because I know how long these would take when you're doing it by hand, but I want you to have the experience of calculating the standard deviation without using the GDC, by using this kind of manual method, because you will be quizzed on it. So only 5 questions for homework. Good luck with that, and we will see you next time.